The 2024 Nobel Prize in Physics honors two pioneers whose work bridged physics, biology, and computation, laying the groundwork for the AI revolution. John J. Hopfield and Geoffrey E. Hinton. They are recognized for foundational discoveries and inventions that enable machine learning with artificial neural networks. Inspired by biological neurons and sharing fundamental similarities with physical systems like magnets, artificial neural networks learn from data. In the early 1980s, John J. Hopfield introduced his influential Hopfield network. This model, drawing on concepts of energy landscapes from physics, showed how a network of simple units could act as an associative memory, storing and retrieving patterns, and even correcting errors. It was a profound demonstration of emergent computational abilities. Geoffrey E. Hinton, over several decades, also made transformative contributions. He co-developed the Boltzmann machine, a neural network that could learn complex data distributions using hidden units. Critically, with collaborators, he championed backpropagation, an algorithm that finally allowed multi-layered neural networks to learn effectively. Hinton then spearheaded the breakthroughs that led to deep learning, devising methods like layer-wise pre-training that made it possible to train the very deep networks powering today's most advanced AI. The foundational discoveries of Hopfield and Hinton are not just behind the AI in our smartphones and search engines. They've also become indispensable tools for scientific discovery itself, from particle physics to predicting protein structures with systems like AlphaFold. Their work, deeply rooted in physical principles, has given humanity a revolutionary new toolkit, profoundly changing how we understand and interact with the world. Every star, a colossal nuclear furnace, eventually exhausts its fuel, leading to some of the most dramatic events in the cosmos. A star's ultimate fate is primarily decided by its mass. Stars like our Sun, after billions of years fusing hydrogen, will swell into enormous red giants. As their core contracts, it briefly fuses helium into carbon and oxygen, but lacking the mass for further fusion, their outer layers drift away, creating a beautiful planetary nebula. Left behind is a white dwarf, an Earth-sized, incredibly dense ember that slowly cools and fades. But for stars born much more massive, 8 times our Sun's mass or greater, the end is far more spectacular. These giants burn through their fuel rapidly, fusing progressively heavier elements until their core is mostly iron. Iron fusion consumes energy, so the star's furnace goes out. Gravity then takes over catastrophically. The core implodes in a fraction of a second, triggering a shockwave that blasts the star apart in a brilliant supernova explosion. This titanic blast scatters heavy elements, forged within the star, across space, seeding new generations of stars and planets. What remains of the core depends on its mass. If it's about 1.5 to 3 times the Sun's mass, it becomes a neutron star, an object of unimaginable density, packing more mass than our Sun into a sphere just the size of a city, often spinning rapidly as a pulsar. However, if the remnant core is even more massive, gravity wins completely. It collapses indefinitely, forming a black hole, a region of space-time so warped that nothing, not even light, can escape. The death of a star, whether a gentle fade or a violent explosion, is not just an ending. It's a crucial part of the universe's ongoing cycle of creation, dispersing the building blocks of life and leaving behind some of the most exotic objects imaginable. The James Webb Space Telescope is peeling back the cosmic dawn, and its gaze upon quasars, the most luminous objects in the universe, powered by supermassive black holes, is rewriting our understanding of the early cosmos. For years, the brilliant glare of distant quasars often blinded us to the galaxies they inhabit, but JWST, with its incredible infrared vision, is finally parting that veil. It's revealing that many of the universe's first giant black holes reside in surprisingly massive and somewhat mature host galaxies far earlier than some theories predicted. We're seeing intricate structures, evidence of vigorous star formation, and even frequent galactic mergers, which likely funneled colossal amounts of gas to feed these awakening giants. JWST is also a time machine, pushing the boundaries of detection to even earlier cosmic epochs. It's finding quasars blazing when the universe was just a few 100 million years old. The existence of such colossal black holes so soon after the Big Bang continues to be a profound puzzle, challenging our models of how these behemoths could grow so massive, so quickly. Beyond just finding them, Webb is dissecting their impact. Its infrared eyes can trace the powerful outflows of gas and dust blasted out by quasars. These cosmic winds can sculpt entire galaxies, sometimes shutting down star formation by expelling fuel, other times potentially triggering new bursts of star birth. This quasar feedback is crucial to understanding how galaxies and their central black holes co-evolve. Many early quasars are also thought to be hidden within dense cocoons of dust. JWST's ability to pierce through this dust is uncovering these previously obscured populations, giving us a more complete census of black hole growth and revealing that the early universe was surprisingly dusty and metal-rich. Even tiny, distant little red dots observed by Webb are turning out to be active galaxies harboring young, growing black holes, blurring the lines between the first galaxies and the first quasars. Each new observation from JWST isn't just giving us prettier pictures. It's providing critical pieces to the puzzle of how the universe's most massive structures and the enigmatic force of dark energy took shape, challenging our theories and opening new windows onto the cosmic dawn. The quest for quantum computational advantage, where quantum computers tackle problems impossible for even the mightiest classical supercomputers, has reached a new zenith. Researchers in China have unveiled Zhuangzi 3, a cutting-edge superconducting quantum computer prototype that is significantly pushing the boundaries of what's achievable. This new machine boasts 105 qubits, a substantial increase, but critically, it also demonstrates exceptionally high operational fidelities. We're talking single-qubit gate accuracy over 99.9%, 2-qubit gates at 99.6%, and readout fidelity exceeding 99.1%. These high-quality operations are crucial for performing complex quantum computations. To showcase Zhuangzi 3's power, the team performed a demanding task known as random circuit sampling. They ran this experiment using 83 of the processor's qubits through 32 cycles of random quantum operations. The quantum computer accomplished the task of generating 1 million samples in just a few hundred seconds. Now compare this to the classical world. The researchers estimate that for Frontier, currently one of the world's most powerful supercomputers, to replicate this exact sampling task with the same fidelity would take an astonishing 6.4 billion years. This isn't just a small step. The classical simulation cost for Zhuangzi 3's experiment is a staggering 6 orders of magnitude, a million times, greater than Google's recent Sycamore experiments. This achievement firmly establishes a new benchmark in demonstrating quantum computational advantage. The Zhuangzi 3 processor, with its increased qubit count, significantly improved coherence times, and high-fidelity gates, was made possible through meticulous optimizations in qubit design, fabrication techniques using a flip-chip approach with tantalum and aluminum, and enhanced noise mitigation. This work is more than just a record-breaking experiment. It provides compelling evidence of the rapidly advancing capabilities of quantum hardware. By scaling up both the number of qubits and the complexity of the circuits they can run, Zhuangzi 3 lays vital groundwork for a future where quantum processors can tackle sophisticated real-world challenges in fields like optimization, machine learning, and drug discovery, heralding a new era of computation. For decades, the engine of our digital age, the transistor, has been on an incredible shrinking spree. Moore's law saw these microscopic switches, the heart of every computer chip, become tinier and more numerous, fueling an explosion in computing power. At the core of each transistor is a gate, controlling the flow of electrical current, separated from the main channel by an insulating layer called the gate oxide. As engineers pushed for smaller, faster transistors, this insulating barrier had to become unimaginably thin, eventually just a few atoms across. And that's where the bizarre rules of the quantum world began to assert themselves, creating a profound challenge: quantum tunneling. Imagine an electron approaching this ultra-thin insulating wall. Classically, if it doesn't have enough energy, it should bounce off. But quantum mechanics paints a different picture. The electron, behaving like a wave, has a non-zero probability of simply passing through this classically insurmountable barrier. It doesn't break the barrier, it tunnels, as if a ghost phasing through a solid wall. For transistors, this is a critical problem. When the gate oxide becomes too thin, electrons begin to tunnel through it, even when the transistor is supposed to be off. This creates leakage current, meaning the switch no longer reliably stops the flow. It wastes power, generates excess heat, and fundamentally limits how small and efficient we can make these vital components using traditional designs. The probability of tunneling is exponentially sensitive to the barrier's thickness and height. The thinner the barrier, the higher the chance an electron will tunnel. This effect isn't just a nuisance for chip designers. It's a direct manifestation of the wave nature of matter and the Heisenberg uncertainty principle. An electron's position and momentum cannot both be precisely known. This inherent fuzziness allows it to borrow energy for an infinitesimal time to penetrate the barrier. Quantum tunneling isn't always a problem, though. It's a fundamental process responsible for nuclear fusion in stars, radioactive decay, and is even exploited in technologies like scanning tunneling microscopes. But for the relentless miniaturization of classical transistors, it represents a true quantum limit, forcing us to explore entirely new materials and computing paradigms to continue our technological advance. Imagine a voyage to a world forged not of rock or ice, but of gleaming metal, a celestial body unlike any we've ever visited. This is the bold ambition of NASA's Psyche mission, a journey to the unique main belt asteroid known as 16 Psyche. This remarkable object, orbiting the Sun between Mars and Jupiter, is one of the largest metallic M-type asteroids, stretching about 173 miles, 280 kilometers, across at its widest point. Unlike its rocky or icy neighbors, Psyche appears to be incredibly dense and composed primarily of metallic iron and nickel, much like Earth's own core. This has led scientists to a captivating theory. Psyche might be the exposed, stripped-down heart of an ancient protoplanet, a planetary building block from the chaotic early solar system that lost its rocky outer layers through violent collisions. Launched in October 2023, the Psyche spacecraft is propelled by an advanced solar electric propulsion system. While en route, the mission team successfully navigated a minor issue with a fuel line valve by switching to a redundant backup system, ensuring the spacecraft remains on its precisely charted course. Its journey includes a crucial Mars gravity assist in May 2026 to slingshot it towards its distant target. Upon its planned arrival at 16 Psyche in August 2029, the orbiter will spend nearly 2 years using its sophisticated instruments to answer fundamental questions. Is Psyche truly a planetary core, or is it a different kind of unmelted primordial material? What are the ages of its varied surface regions, and what does the landscape of this metal world actually look like? Scientists will also investigate its precise metallic composition, searching for light elements similar to those expected in Earth's core, and try to discern the chemical conditions under which it formed. The Psyche mission is far more than an asteroid visit. It's a deep dive into the very processes that built planets. By studying this unique metallic world, we hope to unlock secrets about how planets differentiate, how cores form, and the fundamental building blocks that created Earth and its rocky siblings, offering a rare glimpse into the hidden hearts of planets. At the dawn of the 20th century, classical physics reigned supreme, yet puzzling experiments, like the way objects radiate heat and how light interacts with matter, hinted that reality at its smallest scales was far stranger than imagined. The revolution began in 1900. Max Planck, struggling to explain blackbody radiation, reluctantly proposed that energy isn't continuous, but comes in discrete packets or quanta. 5 years later, Albert Einstein took this further, suggesting light itself consists of these quantum particles, which he called photons, brilliantly explaining the photoelectric effect. The old rules were starting to crack. Niels Bohr then applied these quantum ideas to the atom in 1913, picturing electrons in specific, quantized orbits, explaining atomic stability and spectra, but it was still a partial picture. The true upheaval came in the mid-1920s. Louis de Broglie daringly proposed that if light waves can act like particles, then particles like electrons must also act like waves. This wave-particle duality became a cornerstone. In 1925, Werner Heisenberg formulated matrix mechanics, a radical new mathematics for quantum systems. Almost simultaneously, in 1926, Erwin Schrödinger developed wave mechanics, introducing his famous equation describing how quantum wave functions evolve. Max Born then interpreted these waves, stating their squared amplitude gives the probability of finding a particle, injecting inherent chance into physics. Heisenberg's 1927 uncertainty principle cemented this strangeness. There are fundamental limits to how precisely we can know certain pairs of a particle's properties, like its position and momentum. The very act of observing changes the system. Finally, Paul Dirac unified quantum mechanics with special relativity in 1928, leading to the incredible prediction of antimatter. These breakthroughs, though often counterintuitive, laid the foundation for our modern understanding of the subatomic world, underpinning everything from lasers and computers to the ongoing quest for quantum computing. Quantum mechanics didn't just solve old puzzles, it unveiled an entirely new, probabilistic, and wondrous reality. When we gaze at images of the night sky, we're often captivated by the brilliant tapestry of galaxies, but between these luminous structures lie the universe's greatest, most enigmatic expanses, cosmic voids. These are not just empty patches, they are colossal, underdense regions, the silent giants of the cosmic web. Imagine the universe as a gigantic frothy sponge. The dense parts of the sponge, the filaments and clusters, are where galaxies congregate, drawn together by gravity. The vast interconnected bubbles within this sponge, those are the cosmic voids, and their scale is truly mind-boggling. Typical voids can span tens to hundreds of millions of light years across. To put that in perspective, our own Milky Way galaxy is about 100,000 light years wide. You could fit thousands, even millions, of Milky Way-sized galaxies side by side across a single large void. Some supervoids, like the Eridanus supervoid or the Boots void, nicknamed the Great Nothing, are even larger, stretching for hundreds of millions of light years. While they're called voids, they aren't entirely empty. They do contain some galaxies, often called void galaxies, but these are much sparser and more isolated than those found in denser regions. Interestingly, these void galaxies often appear to be younger and bluer, suggesting they are still actively forming stars, perhaps because they experience fewer disruptive mergers and interactions compared to their counterparts in crowded galactic clusters. Cosmic voids also play a crucial role in shaping our understanding of the universe. Their very existence and properties provide strong evidence for the standard model of cosmology. The way they've grown over cosmic time is sensitive to the nature of dark energy, that mysterious force causing the universe's expansion to accelerate, and even the mass of neutrinos. Studying the subtle distortions of light from distant galaxies as it passes near or through voids, weak gravitational lensing, can help us map the distribution of dark matter. One fascinating, though still debated, idea is that cosmic voids might even exert a subtle push on surrounding structures due to their lower-than-average density, contributing to the large-scale flows of galaxies across the universe. So these vast expanses of near-nothingness are far from boring. Cosmic voids are fundamental components of the universe's grand architecture, holding clues to its past, its evolution, and its ultimate fate. They are the quiet, immense backdrop against which the cosmic drama unfolds. In 2015, citizen scientists staring at data from NASA's Kepler telescope flagged a star that would soon become the biggest mystery in the galaxy. Its name, KIC 8462852, now famously known as Tabby's star. Kepler was looking for the gentle, rhythmic dimming of a planet crossing its star, but Tabby's star behaved like nothing we'd ever seen. Its light wasn't just dipping, it was plummeting, at times by a staggering 22%. To block that much light, you'd need an object 1,000 times the area of Earth. The dimming events were massive, chaotic, and followed no natural pattern. Frustrated, scientists proposed a mind-bending possibility. What if it wasn't natural at all? What if it was an alien megastructure? A vast Dyson swarm of solar collectors, built by an advanced civilization to capture every last drop of its star's energy. The hypothesis was testable. A structure using that much energy should radiate immense waste heat, glowing in infrared light. But when telescopes looked, there was nothing. A major blow to the theory. Then, another clue. During a dip, more blue light was blocked than red, suggesting the culprit was a colossal, translucent cloud of fine dust. But that explanation isn't perfect either. The sheer scale of the dust required is almost impossible to explain, and it doesn't account for another bizarre fact. The star has also been slowly, steadily fading for over a century. This leaves us in a state of genuine scientific suspense. Is a megastructure so advanced, its engineering is silent and invisible to our tests? Could it be made of materials that perfectly mimic dust? The data leaves room for doubt on all sides. The mystery of Tabby's star endures. Is it a natural phenomenon beyond our current understanding, or are we glimpsing the shadow of something constructed? The star keeps dimming, the debate continues, and we are left to wonder what's really out there, hiding in the dark. What if I told you time is not constant? That it's a river that can be bent, stretched, and slowed to a crawl? This isn't science fiction. It's a fundamental truth of our universe, a concept known as time dilation. And nowhere is this effect more extreme than in the presence of a true cosmic monster. Meet TON 618. It is one of the most massive black holes ever discovered, a behemoth weighing 66 billion times more than our Sun. Its shadow is so vast, it could swallow our entire solar system from end to end, 40 times over. Its gravity is so immense, it doesn't just pull on objects, it drags the very fabric of space-time into a bottomless well. So, what happens to time near this monster? Imagine two spaceships. Ship A stays safely in deep space. Ship B bravely travels into a closed, stable orbit around TON 618. From the safety of Ship A, you watch your friend's clock on Ship B, and it barely seems to move. The gravitational pull is so extreme that for every century that passes for you, only a single hour might pass for them. But for the crew on Ship B, everything feels perfectly normal. Their hearts beat once per second. Their clocks tick, as they always do. The impossible truth is only revealed when they look out their window. They would see the universe in hyperspeed. Distant stars would be born and die. Galaxies would spin and evolve. Eons of cosmic history would flash by in what feels to them like an afternoon. They are, in a very real sense, passengers on a one-way trip to the distant future. And if they dared to approach the edge, the event horizon, from your perspective, you would see their ship slow to a halt, frozen for an eternity, as time itself comes to a stop. TON 618 is more than just a massive object. It is one of nature's ultimate time machines, a place where the laws of physics are pushed to their absolute limit and the flow of time is brought to its knees. It was a simple sphere, just 3.5 inches across, a polished ball of plutonium, warm to the touch. Originally slated for use against Japan had the war continued, it was the core for a third atomic bomb. It would never be used in war, but it would still claim its victims. History knows it as the Demon Core. At the Los Alamos laboratory after World War II, scientists continued to probe the limits of the atom. They performed dangerous criticality experiments, pushing the core to the very edge of a chain reaction, a process they called tickling the dragon's tail. On August 21, 1945, physicist Harry Daghlian was working alone at night. While stacking tungsten bricks around the core to reflect its neutrons, he dropped one. In that split second, the core went critical, unleashing a flash of blue light. As Daghlian instinctively knocked the brick away, his hand passed through the intense column of radiation. He had absorbed a fatal dose and died 25 days later in agony. The core, now scarred by one tragedy, was used again. 9 months later, the brilliant but notoriously bold physicist Louis Slotin demonstrated the same test. Known for his cavalier confidence, Slotin ignored safety protocols, using only a flathead screwdriver, his preferred and forbidden tool, to keep two halves of a beryllium sphere separated from the core. Then, the screwdriver slipped, the room erupted in an intense blue flash, a wave of heat and a sour taste of ionized air washed over the men. In a final, heroic act, Slotin used his body as a shield and tore the hemispheres apart with his bare hands, stopping the chain reaction. He knew instantly what he had done. He calmly turned to his colleagues and said, "Well, that does it." He died 9 days later, his body ravaged by radiation. The Demon Core had claimed its second victim. The hands-on, dragon-tickling era of nuclear physics was over, replaced forever by remote-controlled machines. The core itself, a cursed object that had killed 2 of its creators, was finally detonated in a nuclear test, or so they say. Its legacy is a brutal lesson, a terrifying monument to the human cost of discovery, and a permanent reminder that when you work with the fundamental powers of the universe, there is no room for error. Could we ever travel to another star? Not in science fiction, but in reality. Our nearest stellar neighbor Proxima Centauri beckons. It's the closest star to our sun, but close is a cosmic illusion. Proxima Centauri is over 4 light-years away, a staggering 25 trillion miles. Our fastest spacecraft, Voyager 1, would take 75,000 years to complete the journey. Chemical rockets, the technology that took us to the moon, are simply not powerful enough. To cross this ocean of space, we need a new kind of ship. For a robotic probe, our best bet is a laser sail. Imagine a massive, powerful laser array on Earth, firing a beam at a giant, ultra-thin sail in space. The pressure of the light itself would push the sail, accelerating a tiny nanocraft probe to 20% of the speed of light. A project called Breakthrough Starshot is working on this right now, aiming for a journey time of just over 20 years. But to send humans? That requires a far more powerful solution, a fusion rocket, a ship that harnesses the same energy that powers the stars themselves. A fusion drive could, in theory, get a human crew to Proxima Centauri in about 40 years, a voyage within a single lifetime. But even with such a ship, the challenges are immense. The crew would need to be shielded from deadly cosmic radiation. They would need a perfectly closed life support system to survive for decades. And they would face the profound consequences of time dilation. While 40 years would pass for them, even more time would have passed back on Earth. They would arrive at a new star, forever cut off from the world they left behind. So could we ever travel to Proxima Centauri? A robotic probe is almost a certainty within the next century. A human mission remains a multi-generational dream, perhaps the single greatest technological leap humanity will ever attempt. It is a journey that will test the limits of our science, our engineering, and our spirit. But it is a journey that a future version of humanity might just be brave enough to take.